Hello everyone, good morning. My name is Mohammad Jawad Eshki and I'm here with my colleague Hasamuddin Amarpour. Today we are presenting our final project titled Design of a Hybrid Wind and Micro Hydro System for Sustainable Water Treatment. This project was conducted under the supervision of Dr. Ashraf Ali Khan as a part of our Masters in Energy System Engineering at Memorial University. Our aim was to design a renewable energy system suitable for powering water treatment process in remote communities in Newfoundland and Labrador. Let's walk through our research, design simulation, and key findings. In remote areas of Newfoundland and Labrador, communities face critical challenges. Their water treatment system relies entirely on fossil fuel or transport resources, which our report describes as costly and unstable. This dependency creates both financial and environmental burdens. The Canadian government mandates strict water quality standards. If drinking water fails to meet these guidelines, communities must install a treatment system like the one we designed that comply with NSF and ANSI standards 42, 53, or 58. Our target was clear: power a water treatment device that produces 3,000 liters per hour, requiring 5.6 kilowatts hour daily. Based on Canada's average water consumption of 222 liters per person, this system can sustainably serve up to 242 people, enough for a small village. What is the solution? A hybrid wind and micro hydro system. This combination enhances stability and reduces reliance on non-renewable energy sources by tapping into Newfoundland abundant wind and river resources. This isn't just a theoretical. Our Homer simulation, which we'll explore next, proved our words. Let's examine why Camp Brook is the ideal location for this hybrid system. As detailed in our report, this site in Labrador was selected for its abundant freshwater resources and natural landscape, critical for sustainable energy projects. For hydropower, we analyzed 1 year of river follow the data from the Water Survey of Canada. The average flow rate is 0.185 cubic meter per second with consistent net head of 4 meters. Plugging this into hydropower equation, as you can see in this slide, we confirm that a potential output of 7.2 kilowatts. The wind potential is equally impressive. NASA's power platform recorded an average speed of 7.42 meters per second, significantly higher than St. John's with 6.6 meters per second. For a turbine with a 9.62 square meter swept area, this translates to 2.5 kilowatts of power turbine. Together, these natural resources provide a reliable complementary energy base. The hydro system excels in spring with increased flow rate, while wind stabilizes output during winter months. This synergy is what makes our hybrid design valuable year-round. Our system core components were carefully selected for efficiency and reliability in Newfoundland conditions. For hydropower, the reason we choose a propeller turbine is simple design and cost-effective outperforms Kaplan turbines for our site's low head conditions 4 meters and the follow rates averaging 0.185 cubic meters per second. The wind component consists of two annual wind speed 3.3 kilowatt turbine providing a combined 6.6 kilowatt capacity. This complements the hydro system, especially during high wind period when river flow may decrease. Our design illustrates how these components integrate. The AC-DC converter harmonized voltage, allowing seamless power delivery to the water treatment units while charging the batteries during surplus generation. This design guarantee uninterrupted operation, addressing the intermittency in challenge of renewable system. Let's examine the system actual performance. Our Homer simulation reveals a total annual energy production of 33,413 kilowatts hour, while uh, while with hydropower contributing 16,431 kilowatt hour and the wind adding to 18,982 kilowatt hour. The 10 kilowatt hydro turbine operates at an average output of 1.88 kilowatt, running for 7,272 hours annually. Meanwhile, the two wind turbines collectively peak at 8.98 kilowatts and operate for 7,010 hours per year. The battery bank plays a crucial stabilizing role, maintaining its state of charge between 40 to 100% as shown in the figure in a below of the slides. This ensures reliable power delivery during periods of low renewable generation. The energy storage is critical for stability as shown in the figure in this slide. Our 28 battery bank maintains a 48-volt DC bus voltage configured in 7 parallel strings. This setup ensures sufficient reserve power during low generation period. The monthly production chart clearly shows how wind and hydro complements each other seasonally, with hydro production peaking during spring snowmelt, while wind provides consistent output throughout the year. This synergy delivers stable energy for continuous water treatment operations. The water treatment components is rigorously designed to meet Canada's strict standard. As detailed in our project, our system powers a treatment device requiring 5.6 kilowatt-hour to process 3,000 liters per hour, sufficient for 242 people at Canada's average consumption of 222 liters daily. The treatment unit complies with NSF and ANSI standard for 53 for health effects and standard 58 for reverse osmosis system. This certification ensures removal of contaminants to meet Canadian drinking water quality guidelines. This integration demonstrates how renewable energy can reliably power critical infrastructure. The hybrid system's 33,413 kilowatt annual production far exceed the treatment unit's 2,044 kilowatt-hour yearly demand, providing sustainable capacity for system maintenance and peak usage period. Now I'm asking my friend to continue the presentation.
Hello everyone. The environmental advantages are clear. Our report states this hybrid system has a positive impact on the environment by displacing fossil fuels. The numbers prove its economic merit with 33,413 kilowatt-hour annual production. The hydro turbine runs 7,272 hours yearly and wind turbines operate 7,010 hours. The 28 battery storage system ensures reliability while industry standard 25-year life for turbines and treatment equipment make this a long-term solution. Through our report doesn't include exact MPC calculations. The 16,431 kilowatt-hour hydro and 18,982 kilowatt-hour wind production demonstrate sufficient generation to offset conventional energy storage. Our system addresses two key challenges evident in the data. First, seasonal variability. Winter brings higher wind peaking in December, while hydro flow surges during spring snowmelt. This natural is leveraged in our design. Second, technical constraints demanded careful component selection. The propeller turbine was chosen specifically for its simple mechanical structure and lower initial cost, crucial for remote maintenance. The battery banks of 40 to 10% state of charge ensures stability during low generation periods as shown in these figures. The system's architecture turns Newfoundland's climate challenges into advantages. Winter winds offset reduced hydro flow, while spring runoff compensates for a calmer summer. For technical references, our hydro system uses a propeller turbine optimized for 4-meter head and 0.885 cubic meter per second average flow, delivering 16,431 kilowatt-hour annually. The wind component consists of two 3.3 kilowatt turbines taking advantage of the site's 7.40 meter per second average winds, generating 18,982 kilowatt-hour yearly. Energy storage utilized 28 batteries set up for 48 voltage direct current. The hydro and wind power equations shown in previous slides were fundamental to our design calculations. Our turbine selection falls perfectly within the propeller turbine's operational ranges for low-head applications. The water treatment load profile reveals two key patterns from this figure. First, daily demand peaks during daytime operations hours. Second, seasonal recruitment remain stable year-round. At 5.6 kilowatt-hour daily, the system's 33,413 kilowatt-hour annual production creates creates a 31,369 kilowatt extra, demonstrating 15 times our capacity. This ensures reliability during peak demand period, equipment maintenance, and adverse weather conditions. The design easily supports 242 people while accommodating Newfoundland's hard climate through this substantial buffer. In conclusion, our Homer simulations confirm that this hybrid system can successfully and continuously provide the necessary energy for water treatment, producing 33,430 kilowatt-hour annually, enough for 242 people. The environmental benefits are clear with renewable energy creating, creating a positive impact versus diesel alternatives. For future work, we recommend implementing the corrective actions mentioned in Canada's water guidelines through continuous monitoring, expanding battery capacity to cover longer load generation periods, replicating this model in other remote communities with similar wind hydro resources. Our next step could include adding solar PV for redundancy or microgrid integration. We hope that this design can serve as a blueprint for future rural electrification and clean water projects. Thank you for your attention. Also, this slide you can see the reference. Thank you for watching our presentation.